Okay. Hello, my name is Emmeline Fisher. I will be presenting the paper POTUS, Probing Off-the-Shelf USB Drivers with Symbolic Fault Injection. I would like to thank the authors James Patrick Evans, Lorenzo Collaro, and Johannes Kinzer for their excellent research and the USENIX workshop for making this paper easily accessible. So, first some background information to make this easily understood. Client USB device drivers have many software bugs. Device drivers generally have more bugs than any other part of the Linux kernel. In one study, 70% of Linux device drivers had an error rate that was 3 to 7 times higher than the core kernel. This is due to many different types of USBs and the lack of continuous maintenance as devices age. USB devices can be used to spread malware, even to air-gapped devices. These drivers have a high level of privilege, which obviously makes them prime targets. And these vulnerabilities can lead to denial of service, and even in the worst case scenario, multi-step exploits. So, defense techniques. There are many defense techniques that are currently available. These include kernel address space layout randomization, KASLR, data execution prevention, DEP, return address protection, RAP, system mode execution prevention, SMEP, system mode access prevention, SMAP, and control flow integrity. These, of course, help a little bit, but do not prevent all attacks, as we will see from this research. Current methods to eliminate bugs include testing and static analysis. Current testing methods that are available focus on the core USB module, USB core, instead of drivers. The authors wanted to focus on the drivers because they believe that the current methods are an incomplete approach. And basically, yeah. So another tool is Coverity, which is a mature static analyzer that scans the Linux kernel often. Of course, it still misses bugs based on the runtime environment and hardware, and it also misses bugs that are based on complex and simultaneous interactions that occur between multiple components. So, probing off-the-shelf USB drivers with symbolic fault injections, or POTUS, which is how I will be referring to it from now on, is primarily focused on finding deep bugs that result from complex interactions with the matching hardware USB. So the author's attack model is someone that has physical access to the USB port and guest privileges. This would be, so in the real world, someone who's plugging their custom USB with the code, exploit code on it, while another user is logged in. The authors created a design to find bugs in the device drivers, and so POTUS is a combination of fault injection with concurrency fuzzing and symbolic execution, all wrapped together. They explored faults that were relevant and ignored the repeated ones, which will be explained later, and they were able to find 2 zero-day vulnerabilities in the drivers out of the Linux kernel using POTUS. So they also came up with a method to simulate a virtual USB device, which allowed them to test arbitrary client drivers. Actually, with this generic USB device, they were able to simulate any type of USB they wanted. And this was built out of the QEMU virtual machine. So some key concepts: selective symbolic execution, which I will be calling S²E, which is what they came up with based out of this. It's centered on interpreting a program on symbolic rather than concrete real data. And the instructions will manipulate symbolic expressions rather than actual values, allowing them to explore many errors at once. Variables are expressed as symbolic endpoints at any point during the program's execution. With conditional instructions, they are interpreted by computing symbolic expressions, which then fork the program state, and the outcome is recorded in a path condition. An issue, of course, is path explosion, but S²E deals with that, and basically what it does is that it prevents the exponential growth in number of paths that exist by switching between concrete and symbolic execution. So the symbolic data is injected into random memory addresses, and each code block manipulates the symbolic data that is, and then that's symbolically executed. So the USBs. USBs have many features, which include hot plugging, generic class drivers, multi-master USB on the go, and data and power transfer modes. It follows the master-slave protocol with a host controller interface, HCI. This communicates with USB client devices. HCIs implement low-level protocols, which include timing, packet scheduling, and signaling. The Linux kernel has a USB subsystem that allows new client drivers to interact with hardware without much effort. USB enumeration. So Cubed is a kernel daemon thread. It monitors USB hubs by communicating with onboard HCI and configuration of USB devices. Whenever a USB device is connected to the machine, the kernel establishes its capabilities and configurations. This is called USB enumeration. It iterates over the configuration descriptors, and it decides how it would deal with like transfer types, power output, speed, device class, etc. So when enumeration is finally completed, the USB client driver is then able to communicate with the device via a library function in the USB core. These are sent out as URBs, which I'm going to be discussing in the next slide, to HCIs and then sent on to a gadget. So universal request blocks. These contain the device addresses that signify the devices connected on the bus. They also have endpoints that specify the channels to the device. The four types of URBs are control transfers. These handle device configuration and signal control information. Bulk transfers, which deal with large quantities of non-time sensitive data. Interrupt transfers, which are focused on small quantities of time sensitive data. So it's the opposite of bulk. And isochronous transfer, which handles real-time data at bit rates that are predictable. So this is a schematic or the architecture of the POTUS. The USB driver is in the VM and receives input from a driver, exerciser, and USB devices. These USB devices are connected via the QEMU, Universal Host Interface. The USB devices were actually virtual in this study. The driver exerciser runs in the guest and establishes the possible different interactions of the user with the device. Data that is sent from the device is symbolic. This allows them to explore the response from the S²E. Faults are visible in the form of symbolic arrow codes. SystemTap script allowed them to interact between guest and code in S2E. They use these scripts to inject data at function calls or return sites. S2E plugins were used to prune paths and state tagging. This was the way that they limited path explosion and were able to focus on exploring different faults, like deep bugs within the program. They used many existing tools, some of which are kernel address sanitizer, KASN, which allowed them to deal with memory errors. Kmemleak, which was for obviously memory leaks, and kernel thread sanitizers for database. This did add a lot of overhead to their performance though. So the USB device, a USB generic device that they used was virtual. The device descriptors were configurable, and it allowed for them to allowed for a symbolic method for data transfer. The 5 descriptors are string, device, configuration, interface, and endpoint. This generic device is able to impersonate any USB device by changing its descriptors and its configuration files. So once they configured the descriptors, the USB device was used to test the driver. The USB generic device used in the study ignored content out of the URBs in response to in URBs. They write and mark requested amounts of data as symbolic for S2E. These URBs could be customized if desired, but this was not done in the study. The USB device can be instructed to respond negatively or intentionally violate what was specified, like typical specifications that they would have for USBs. SystemTap automatically injects SystemTap is used by POTUS to inject faults into the kernel. It places probes in arbitrary kernel locations that gather intel. It can also inject compiled C code to modify kernel data structure. POTUS also has SystemTap automatically inject faults into kernel submodules. These are being used by the USB client device driver, for example, the USB core. Because of fault injections, the current state splits or forks, and one state will return the success and another will return like a symbolic error code. So with the symbolic fault injection, they're able to explore all the codes at one time, and this also they also injected maximum allowable delays, which allow them to expose like concurrency bugs. The driver exerciser. The driver exerciser starts the operations on the device. It'll randomly start file operations on the target device file descriptor. It exposes concurrency bugs by starting many simultaneous operations on the same or different file descriptors. So this figure illustrates an execution path for a guest user. So basically, they are opening a device that is owned by the Goose B Tower driver. So the user calls the sysopen on the file, and this calls back. This opens a map that calls back to within the aforementioned driver. When the driver tries to allocate memory or like call the kernel subsystems where the fault injection is active, the POTUS system state will then be forked. POTUS will then, the system state will then fork and the symbolic fault will result. The fault-free path continues on and then forks again. And yeah, as you can see, it fails to transfer after the delay. So, the authors focused on deep bugs that arise from concurrency errors. They believe that the other bugs likely had already been found via static analysis. So, they prioritized paths that didn't have faults or delays in them. So, like it would fork off. So, one path would fork off and it would have like a fault. They would go with the path that had no faults. And this spawned new states that could possibly have injection points or delays. POTUS actually attaches a map of annotations to each state, and this map is cloned every time path forks. This allows them to track the amount of faults and children that they've created, and it also allows them to limit the number of fork points. And once the limit of faults was achieved, they stopped because they believed that paths with high numbers of faults were they were going to likely lead to exploring the same paths, the same code many times, and it wouldn't have been very useful. So, AirSpy. So the authors were able to find 2 zero-day exploits. One of them was when the USB device driver communicated with the AirSpy software-defined radio, SDR. This memory leak can be triggered from hardware and can perform a denial of service attack. The host crashes when a custom USB device is inserted into the computer. That triggers this. And the device driver interacts with video for Linux 2. It needs the v412 device structures and its registration. This error is actually within the probe function, and it is called when the USB device is inserted into the host. And you can actually see this to the right, this error. So, this is installed by default on most Linux computers. So, yeah. Whenever a USB device with AirSpy descriptor is inserted, this module loads. The video register device will fail. So one of the ways this can be exploited is when, because it will only support 64 devices, and if the USB device is actually created to act as a hub, and they add 65 devices that are attached, this actually triggers a denial of service attack. So, this is the second second zero-day vulnerability that the authors discovered. It is in the Linux kernel's Lego USB tower driver, which has been around since 2003. It is a race condition, which leads to null pointer dereference. If this is remapped to a user-controlled memory location, it can actually be used to increase privilege or execute whatever code the attacker wants. So to the right, you can see the code where the vulnerability is located. The function registers the character device file, then requests the firmware version. So if the URB request fails, it then calls tower delete, and this deletes device structures, and which are actually associated with the driver, and no attempt to check for any active connection is made. So if the device file is registered before the probe function terminates, then it will allow you to be able to access files from the user space. So here's another snippet of the code that has this vulnerability. Here it's the tower write function, and it maps to the sys write call. It will check if the device is still connected before copying data from the user space into the local kernel buffer. The tower delete called after the write function to check that device is connected, and the dev structure will be deleted, and its value will be set to null. This causes a null pointer dereference in tower write. So then the attacker can map the null page to control the location of the data, and since they control this location, they will then be able to write arbitrary code that, like, whatever they want. And so this overwrites this can overwrite the local user ID and ultimately gain root privileges. So in modern machines, they were able to like bypass. So the authors had tried this in more modern machines too, and they were able to bypass the SMEP, SMAP, and RIP, but they had to relax their conditions, and they actually ended up creating a kernel module that actually first leaked the memory addresses, which allowed them to bypass KSLR. So, and then they were able to basically do this. But yeah. So some limitations of POTUS is that the USB generic device does not support many of the newer features like USB on the go, since it doesn't have multi-master setup. But there is also a high runtime overhead for the symbolic execution, which increases the timer interrupts, and they actually had to slow the QEMU internal clock because they're having so many of them. So those are some of those problems. And then in conclusion, POTUS is still a work in progress, but it has found bugs that have existed for long periods of time that other tools were not able to discover. It can be used with other projects since it's open source, which is great. Thanks for listening to my presentation. If you have any questions, feel free to ask in Piazza. Thanks.